Today we'll be multiplying binomial special cases. In our first example, we'll be dealing with the difference of squares. And this gets its name from the fact that we are using the same values and same variable, but we are using the opposite sign. So in this case, where we have 2, a positive, we're going to use a -2. Now, if I were to just go through the steps to show all my work, I would show that I am multiplying my first terms, giving me x squared. Multiply my next terms, the outside, which gives me a -2x. My inside terms, which gives me a positive 2x. And then my last terms, which will give me a -4. Now with this, we normally combine our inside terms. -2x plus 2x cancels out. They end up giving us 0x. Since this is a value of 0, I do not need to show it, so I'm left with the x squared minus 4. Now this is the simplified version. There's nothing else that I can do, so this is my answer. Now this does follow a specific pattern. If we look closely, what we did was we squared our first terms, and then we squared our last terms, subtracting it. This is what we call the difference of squares. In using this pattern, we can follow this equation to the side. Anytime that we are using the difference of powers, we have the same value as the first and the same value as the second, but one is subtracting, one is adding. We can follow where we just square the first term and we subtract squaring the second term. For example, if I were to use this and label all my parts, my x would be my a, and my b's would be the 5 values. Now I could label these as well, but they are the same values. I would be just labeling them a and b. So instead of going through this step where I have to distribute everything and showing my work, I can follow this rule up here because they are difference of squares. I know I need to take my a value, which is x, and it needs to be squared. And I need to take my b value after subtracting, and I need to square it. In this case, would be 5 squared, which is 25. I can write that a little bit better. Now with this shortcut, with this rule, I've already come to my answer. I did not have to write down the middle step after distributing everything using double distribution. Now it could be a little bit more complex. You may need to add to that. I need to realize that for number 5, that my a is going to be 3x. And my b, in this case, is 5. So understanding this, showing it out, and following the same rule, I'm going to take a squared. I'm going to square the 3x. 3x squared will give me 9x squared. And then again, showing that I'm subtracting my b value, that is squared. 5 squared is 25. So in this case, this is using the difference of squares so that I can shorthand the amount of work that I need to show. Instead of double distribution, multiplying the 3x to both terms, and then the -5 to both terms, and combining like terms, I notice that there is a pattern that cancels out my x term, and it leaves my a and b squared. Another special case is our perfect square trinomials. Starting off with number 7, if we look at this, we have x plus 3, and this is all squared. If we remember our rules of power, this simply means that I'm going to multiply x plus 3 times itself. If I follow my steps, I get x squared for my first term. I get 3x for my second term. Moving on to the next part of double distribution. 3 times x, yet again, is 3x. And then my last portion, 3 times 3 gives me a positive 9. So this somewhat follows our difference of squares rule. If you notice that our first portion is still squared, our a squared, and our last portion is still our b squared, our second number squared. Oh, I did not write this completed. 3 times x is 3x, and then we have plus 9. So I was saying the first and last portions are still squared, but now I have this piece in the middle. When I combine my like terms here, I still have the x squared up front. But now this is 2 of 3x, which gives me a 6x. And then I still have the plus 9 at the end, the 3 squared. Now there are no other terms that I can combine. There's nothing else I can simplify for work, so this is my answer. In this case, if I look at this, I still have the a squared portion, my first part squared. I still have the b squared portion, but instead of canceling out whenever we have the difference of squares, we are actually doubling the amount of our a times our b. So in this case, our a being the x and b being the 3, and then I multiply that by 2, which is our first equation on the side. Now, if this was negative, you would do the same steps, but this part would be a negative value. So to try to put this into the process, this is a negative. This means that I'm going to use the second equation. Just to write down my parts, my a is x. My b this time is going to be a 5. So I'm going to fill in this equation. My a squared is now going to be x squared. I'm going to multiply my pieces together. So 5 times x is 5x, and then multiply that by 2. Gives me a 10, a negative 10 in terms of x. And then my last piece is to add my b squared. So I'm going to add 5 squared. And in this case, I'm done. I can see this being a squared. If I square one side, I square the other. I can see the end being b squared. 5 squared is 25. And then my middle piece is double the product of a and b. Give me 5x. Doubled, it gives me 10x. I can do this on a little bit more complex part where a this time is 2 parts to it. My a is 2x and my b is still just one number. I still follow the rules. I'm going to take a squared, which gives me 4x squared. I have to multiply every part of the term. My middle part is going to be the values multiplied, a times b multiplied. 2x times 1 is just 2x, and then double it. Which gives me 4x. And then the last piece is I'm going to square my b value. 1 squared is a positive 1. Now that I've finished following the pattern, I cannot combine any more terms. I cannot simplify anymore. This is my answer. So, if you get comfortable with the patterns, you can use our 2 rules for perfect square trinomials to make the work a little bit easier. Or, in this case, for difference of squares, you can use the 1 rule in order to simplify how much work you have to do. Instead of writing all this work, all the lines included, to visualize the double distribution, I can just go directly to an answer. And that is the point of figuring out patterns in the work that we do.